You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Peter Gorham. Dr. Gorham is a professor of physics at the University of Hawaii. His research focuses on the detection of high-energy particles, as well as the measurement of the Askarine effect, in the effort to detect ultra-high-energy neutrinos using Anita, the Antarctic Impulsive Transient Antenna.
Peter Gorham, welcome to the program.
Hello.
Doctor, tell us about your experiment, Anita.
Okay, so the Anita is a long-duration balloon payload. It's flown by the NASA Columbia Scientific Balloon Facility. This is NASA's scientific ballooning arm, I guess you would call it. And Anita stands for Antarctic Impulsive Transient Antenna. It's actually a collection of antennas sort of grouped into this one mega antenna, if you will, which flies above the Antarctic ice sheets and listens for very sharp bursts of radio emission that may be arising from the ice sheets. And of course, we wouldn't expect bursts of radio emission in Antarctica unless, there were people with walkie-talkies or something like that. But we know that cosmic particles will actually arrive at Earth, and one particular particle that we're interested in, the neutrino, can actually penetrate into the Earth and enter the ice and deposit its energy through an interaction with a nucleus in the ice sheet. And that'll make something like a little lightning bolt inside of the ice. And that neutrino lightning bolt then can be detected from a payload flying above Antarctica. So this is, and Anita represents an effort to try to detect astrophysical neutrinos. And we've been doing this for, it's almost 2 decades now. I'm surprised myself at that. And it has involved a lot of trips to Antarctica to make it happen.
Now, about these particles that are coming upward from the ice, seems to me that the sun is probably not the source of that, right? So is there any idea where, why neutrinos would be coming up from that direction?
As we fly over the ice sheets, we actually see, as we're looking down at the ice, we see many, many different directions on the sky at the same time. We're sort of sensitive to a major part of the sky. And we believe that astrophysical transients like supernovae or active galactic nuclei, quasars, these very energetic objects that appear throughout the cosmos, we believe that these things are effectively high energy particle accelerators. And we see the results of that acceleration raining into the Earth all the time in the form of regular subatomic particles like protons or nuclei. And those we call cosmic rays. And those have been measured for many decades. But neutrinos are a relatively new part of this panoply of particles that we can measure from outer space. And they have an advantage over normal nuclei in that they can penetrate right through other materials, which a proton cannot. It'll crash into material right away and stop, which is a good thing for us because our atmosphere protects us for the most part from these very intense kinds of radiation. So neutrinos could be coming from a source that happens to be in the direction which is beneath the ice, and that's usually a good thing for us because the neutrino will interact and then we have a chance to see that effect in that kind of burst of radio waves. The difficulty that the sort of recent studies have pointed out, though, is the direction that we saw these particular events from was too deep in the ice. That is, we're looking down at the Earth, and if you imagine that track passing through the Earth, it actually went through too much Earth even for a proper neutrino. We believe we know the theory of these neutrinos pretty well, and those neutrinos from that deep in the Earth should have been completely blocked. We can see neutrinos potentially from closer to the horizon, but as you go deeper and deeper in those directions, down through the Earth, then we shouldn't see them at all. So that was kind of the difficulty, is we've seen something that is from a direction that we should have been blocked.
Is there room in the standard model for a new type of neutrino?
Well, there is actually. Neutrinos are a crazy kind of particle. They have many properties that no one ordered, and we keep discovering new things about them. One possibility is that we may have neutrinos which have a different, what we call handedness, to the normal neutrinos, which from physics convention we call left-handed neutrinos. So it's possible that we have partners to the existing families of neutrinos that are what are called right-handed neutrinos, and these could be very, very heavy particles, much heavier than normal neutrinos, and may have very different kinds of interactions, including the ability to penetrate through much more material. But we just don't know right now. There are some fairly significant limits on right-handed neutrinos, but we can't exclude that they're possibly there, because so much about the neutrino world is strange and unexpected, I think.
And not to mention very, very difficult to study when you're looking at something that's not that interactive. How does your experiment actually detect? You just detect the radio waves from the interaction of the neutrino and something else, right?
That's right. So the neutrino will, as I said before, because the neutrinos we're interested in have quite energetic, they're very high in kinetic energy. When that neutrino interacts with an atom, which it won't do often, but still can do if you throw enough material in its way, it will interact eventually. And what happens then is the energy from that neutrino, which is quite enormous, comparable to a major league fastball in kind of packed up into a single subatomic particle. That energy can be converted into secondary matter itself with very high energy, and this takes place through Einstein's famous equation. Energy is mass times the speed of light squared. And those secondary particles themselves can sort of create even tertiary particles in the form of a cascade. And the voltage that you can relate to that cascade is extremely high. The neutrinos that we're looking at have an effective energy voltage, if you will, of order 1 billion times 1 billion. Physicists use these units called electron volts for energies that high. And if you take that neutrino and collide it with a particle, then the lightning bolt that results is something like 1 billion volts of lightning. And that then kind of blasts its way through the ice. It probably can only go about 10 meters or so before it dissipates. But in that 10 meters, it produces a very intense burst of radio waves with very specific properties. And so by sitting above the ice, we can watch for these intense radio bursts, measure their polarization, their energy spectrum, their time spectrum, and all these detailed properties, and then we can assign it back to the original particle that may have caused it.
Now, what of cosmic rays coming in from the opposite direction, from space? Some of those have been shown to be extremely high energy. I think there was the oh my god particle, I think is what they called it back in the day. Could this be related to whatever's creating high energy neutrinos?
Yes, in fact, it's very likely to be closely related to that. As these high energy cosmic rays propagate through the universe, they have a problem. And that problem is something called the cosmic microwave background radiation, which fills the whole universe with photons, microwave photons. And these are the sort of echo left over from the Big Bang. But if you happen to be riding on a cosmic ray particle, if you could do that somehow at the speed of light as it's moving through the universe, from your point of view, your frame of reference, these microwave photons, which are very cold, they're about 3 degrees Kelvin in temperature, if you will, they actually look like gamma rays to you because you're moving so fast. So you look out and you see this fire hose of gamma rays in your face, but in fact, from the point of view of the universe, the cosmic ray itself is the thing which is running very hot. However, what that means is that cosmic rays can't go very far, maybe only the distance a few times, a few tens of times the typical size of a galaxy, a cosmic ray will collide with one of these photons and it will make its own cascade of secondary particles out in the cosmos somewhere. And some fraction of those secondary particles are neutrinos. So the neutrinos that come from these cosmic rays represent the flux of particles that is very interesting to us. At the same time, we actually do detect the pulses, radio pulses from the high energy cosmic rays as well. And those are kind of raining down, and we observe those from above the ice and also reflected off the surface of the ice.
Interesting, reflected off the surface of the ice. Huh. Now, one thing about neutrinos and a neutrino flux came up recently with the dimming of the great dimming of Betelgeuse, which led some to speculate that it might be getting close to supernova, which it obviously wasn't. But had it done that, there would be a neutrino pulse that would be the first indicator that a star exploded. Now, what experiments do we have going with neutrinos that would tell us, that would actually tell us that a supernova just went off and we need to point the telescopes at it?
Very good question. Well, so Anita is not a very good detector for supernovae because what we're not sure about is whether supernovae also produce very high energy neutrinos at this sort of billion electron volt level. What we do know is they produce neutrinos at the million electron volt level, and they make them copiously. So this burst of million volt neutrinos will arrive at Earth over some period of time, maybe just a few seconds or perhaps a bit longer. And the kinds of detectors that can see those are not so much the Anita type detectors, but detectors which, for example, there's one in a mine in Japan called Super Kamiokanda. I think actually the latest version is called Hyper Kamiokanda. These are very large volumes of water, tens of thousands of tons of very pure water. And they fill that water volume. This is in a giant vault in a deep in a zinc mine in Japan. That volume of water is filled with ultra-sensitive light detectors. And when those neutrinos from that supernova interact in a volume of water like that, they actually produce a number of secondary cascades, small ones. But hyperkamiokanda and similar detectors are designed so that they can detect that and they can measure the direction. And so they would be able to immediately alert us that we have a potential supernova. And if this were to take place in our galaxy, I think it would be quite dramatic in such a detector.
Indeed, and would give us a probe into the first moments of a supernova. Now, I want to ask you this, Doctor. You're working in radio. Are the frequencies you're looking at something that humans can interfere with? Do we broadcast at those frequencies?
Oh, yes, indeed. This is our toughest problem. Even in Antarctica, where there's only at most a few thousand people across the entire continent, during the austral summer when we fly our payload, we are predominantly measuring just the impulses and squawks of radio signals produced by human beings. When we take our data at the end of a flight, which is typically maybe 4 to 5 weeks long, we'll see something like a million or more, maybe 2 or 3 million events associated with human activity. And from that, we expect to, at most a handful of those might be associated with neutrinos. So we have to be very, very picky in selecting the events out and trying to eliminate all of the human-generated noise. In addition, there are satellites that are in geosynchronous orbit, and we have to eliminate noise from them as well. So our world is a world that's kind of buried in radio noise. And for those of us working in radio science, one of our biggest challenges is to sort of try to turn all of that off for some period of time when we try to do our science.
Yeah, imagine being a SETI researcher with a radio telescope trying to pick out a signal from an intelligent civilization right in the middle of an intelligent civilization.
It's very difficult.
Now, Doctor, Antarctica, which is I can't think of a place on Earth that's more interesting and mysterious than this almost uninhabited continent. What's it like working down there? I mean, it has to be difficult to get your experiment down there and in the air.
Yes, it is. It's a long process. It starts with we start our effort in Texas, where we integrate our payload at a NASA facility. Then we sort of gather it all up, pack it away into shipping crates, ship it down south to Christchurch, New Zealand. And at some point then we all fly down to Christchurch. Payload usually precedes us by a month or two and is set up on the ice out usually in the open where we have to go and fetch it. When we arrive in Antarctica, it is a spectacular place. There's nothing like it on Earth. It takes your breath away that first moment as you get off the aircraft transport to get down there. Usually we're arriving at a place called Williams Field, which is on the Ross ice shelf, and directly in front of us, maybe 20 miles away, is an enormous active volcano, completely covered top to bottom by ice, by glaciers that are nothing like anything you've ever seen before. They are absolutely stunning.
Out of curiosity, is the volcano Mount Erebus, I think?
Exactly, yes. And it is something that you have no perspective when you're working down there for the distances which you see. It's because we don't see any of the normal things that give us the sense of distance. You can be standing 20 or 30 miles away from this volcano and still feel like it's a half-mile hike away from you. It's a sort of a strange effect. The other amazing thing, of course, when we worked in the austral summer, is the sun is up all day long. It just circles the sky, and so you have a difficulty telling what time it is. And of course, some people have great difficulty sleeping. Even if you darken your room, it's hard to hide all the sunlight. It's extremely dry. That's another difficulty for us to work down there. There's nothing really living except what we bring, and maybe a few lichens, I think, over in one of the valleys. But other than, well, no, I take it back. There's some wildlife. There are seals, some birds, and sea life, of course. But it is a pristine place, unlike anything else that we normally experience in our lives. And working at the South Pole is another step entirely. It is so desolate and so strange there that psychologically you have to cope with the isolation and the extreme cold when you're up at the South Pole. So it is truly one of the last frontiers on Earth and a wonderful place to do science.
One wonders about the people that hold down the fort down there during the dark, where Antarctica becomes cold and dark, and you're just sitting there at McMurdo or something like that, where you just have 1,000 miles of flat ice around you.
It does take a special kind of person to do that, and of course it's very interesting either at McMurdo or the South Pole to talk with some of the veterans who have done many seasons, many what we call a winter over, and they have their own kind of unique character that's prepared and sort of fired up for that. And some of the stories are really truly amazing. So although it's not something I think I would ever have the guts to do, I do greatly appreciate these guys who are willing to, as you say, hold down the fort.
Now, the Ross Ice Shelf is always big news because of climate science. Have you seen any evidence there of change over the times you've been there?
I think the main thing that I've noticed is it seems to me that we actually do feel that the average temperatures are noticeably different. I think when I first went back in about 2005, I felt like we just had more colder days. And I think the problem is that as a scientist, I question my own experience because I know that things are getting warmer, but I also have a tendency to believe that it's true. The work that we do, we don't come in direct contact with, the obvious changes such as this, the calving that's going on in some of the ice shelves. But we hear about it, and we hear about the concern from our fellow glaciologists And it is, I think, very sobering what we're seeing down there. It seems that every time we make a prediction about the rate of climate change, we manage to underestimate it. I can't think of a single thing that has been overestimated. Scientists, we try to be very conservative, but in this case, I think our conservatism has perhaps done a disservice, because it is something that all of us need to be very concerned about, the possibility that these effects are accelerating and have gone beyond the point where we can rein them in.
Now, Doctor, to switch gears back to neutrinos, there was a lot of buzz about these Antarctic detections of neutrinos, and there was also a lot of misinformation outright in certain sectors of the media that this somehow suggested the existence of an alternate universe. What's wrong with that? What went wrong?
Well, I on the one hand, they say all press is good press, and perhaps you and I wouldn't be talking if that had not happened. So, I will take that as the bright side of all this. I think what happens sometimes is there's a lot of pressure to get things out into the public, where all media are competing with limited resources for people's attention on this hyperactive network that we all share. And so in this particular case, I think there was a quite excellent study that was done about the possibility that some of our signals might be associated with a theory that proposed, in effect, this particular theory was trying to explain the asymmetry that we see in the universe today, that we see far more matter than antimatter. And one of the possibilities is that there's, in effect, a universe and an anti-universe, and we lose contact with the anti-universe very early on after the Big Bang. And we stay in the universe, but the anti-universe is still out there. And one of the consequences of that theory is that you will get these heavy right-handed neutrinos in our own universe. Those heavy right-handed neutrinos are something that could be associated with the signal that we see, although I personally don't know if it's the simplest explanation for what we've seen. However, it doesn't mean that we're getting contact with this anti-universe or parallel universe. There is no connection between us and it anymore. Once they separated at the Big Bang, they were completely separate, if in fact that was the explanation. But I think the media that first reported this didn't have the time to check all of these subtle distinctions, and the report was that NASA scientists had confirmed a parallel universe, which really was completely misguided. So I think since then that there's been some more sober understanding of that, and an idea that is, I think, interesting. I actually believe that reasonable scientific free speculation is a good thing, and it helps us to sort of figure out what is and what is not possible. But in this case, probably the best thing to apply is this famous idea of Occam's razor, in which the simplest explanation is likely to be the best one. The problem right now is we don't exactly have a simple explanation yet for everything that we're seeing in our data in Antarctica. But the idea of the anti-universe and the right-handed neutrinos is probably one of the more complex proposals to address that. So I don't know if we're quite ready to sign on to that yet, but I think it's still an interesting idea, and taken with some sober thinking is certainly worth exploring.
And I think, the generally, this is a new theory, but the generally not accepted but advanced one is that the Big Bang simply created more matter than antimatter, and that it annihilated and we're what's left.
Yes, and there are other ways to create that asymmetry, even though the universe anti-universe idea that was put forth by some physicists, including Neil Turok, even though that is an elegant idea from the point of view of physics, it may not be the most acceptable one. There are other ideas out there from the realm of particle physics. Certainly none of this has been demonstrated or proven by any stretch. So in that regard, the tabloid headlines were I think, jumping the gun pretty dramatically.
And I hope that doesn't take away from the actual research, because there are a lot of mysteries involving neutrinos that are going to be it's going to be interesting to find out exactly what's going on and why some of them do this.
Yeah, I think, neutrinos by themselves are bizarre enough and interesting enough, and in some sense, they almost already exist in their own parallel universe, although it's not quite separated from us. I mean, in the neutrino realm, a trillion solar and cosmic neutrinos are passing through the tip of your nose every second, and you don't feel them at all. The entire universe is chock full of neutrinos in every square centimeter, and we don't feel them in any way or shape or form. So it's not so much of a stretch to say that neutrinos by themselves already constitute a parallel universe of very strange and interesting particles, but we can demonstrate that they really exist, and we can do research that is well documented on their characteristics and properties.
And here we are in cosmology, because if you can barely detect a neutrino, what can't you detect, i.e. dark matter?
Yes, dark matter is a really tough problem. Interestingly, one of Neil Turok's ideas with his anti-universe approach was that, in fact, he wasn't trying to explain Anita events, but he was trying to understand dark matter. And the heavy right-handed neutrinos that he postulates in that theory actually could be a dark matter candidate, strangely enough. But dark matter is one of the most difficult and most outstanding and most compelling problems that we're facing in astrophysics and cosmology, and one that is sort of always in everyone's back of the mind, thinking about whatever they're measuring. I don't know if Anita has anything to do with dark matter, but if it does, then that will be certainly a wonderful surprise.
Absolutely. Well, thank you for appearing with us, Doctor, and good luck on your next trip to Antarctica.
Thank you so much for having me, and good luck to you guys, and everybody stay safe.
Thanks for watching Event Horizon. If you like what you see, feel free to subscribe. And if you'd like to be notified of future videos, you could always ring the ding-a-ling. And that was the wrong bell.